in connection with the project, the flow project, we were asked to graph the quadratic function that represents the depth versus clock time from one of our observations. And or we were asked to graph actually the function we have here and another function that might represent two different sets of observations, possibly with different conditions, okay? And nobody seemed to know how to graph a quadratic function. Of course, it's been a little while since we've talked about this, so we need to review a little bit, but I'm not going to say too much about this, except to say that, remember, the quadratic formula tells you that a quadratic function has zeros at x equals negative b plus or minus the square root of b squared, etc., and that halfway between the plus and the minus we have just negative b. So in the numerator, negative b is halfway between the numerator of the two zeros, and they all have the same denominator. And the graph is symmetric about the vertical line through the vertex, so that the x position of the vertex, or if you prefer the axis of symmetry, is at negative b over 2a. And this is something, again, we did thoroughly some time ago, so you need to review this. Okay, so right here is that position. So the vertex is at this x position, and we get the y coordinate by plugging this in to the function. Okay, now I'm using x here and I've got t here. I wanted to use x because that's the way we remember the quadratic formula if we're working from memory. But of course, in the case of this function, we would be graphing y versus t and not y versus x, so I'm going to make those t's. And then, actually I persisted with the x here, but I had y of t, so I should have had a t there. Y of t then is a times t minus h squared plus k. Now I had x here because we're familiar with the a times x minus h squared plus k form, or we should be familiar with that, graphing by transformations. So we could transform the y equals x squared graph, but now I'm going to call it the y equals t squared graph. Vertical stretch by factor a, horizontal shift of h, vertical shift of k. This is how we graph one of these functions. So we should be able now to graph this function, and just going over the steps again. A is 0.02, B is negative 1.5, C is 100, so that our t coordinate of our vertex is negative b over 2a, and that's going to be the negative of our b, which is negative 1.5 divided by 2a, 2 times 0.02. That comes out 37.5. The y coordinate of the vertex, what do? We plug the value of t for the axis of symmetry, which is where the vertex is. We plug that value of t into the function, plug it into this function, we get this, and it comes out 71.9. So now we have a graph of this function. Y-intercept, the coordinate of the vertex, 37.5, 71.9. Okay, that's this function. Now, this function actually gives us a parabola, but the only part of the parabola we're really interested in is the part between t equals 0, which is presumably where we start, and where we reach the vertex, because at the vertex the water stops going down. In other words, the y values stop going down and come back up. Now as water flows out of that cylinder, water comes down and it stops. It stops at the vertex point. So I put a little wavy line through this part of the parabola to indicate that this is not in the domain of this function. Okay? Now, if we have another function, and there was a second function, something like 0.025 t squared minus 1.4 t plus 110. Question was, if you got two cylinders, and y1 of t describes the depth of this one, and y2 of t describes the depth of this one, are the two depths ever equal? Now, that's obviously not always the case, except maybe if they stop, if this one stops before this one gets to that point, or vice versa. But in general, if they stop at the same point, let's say, they won't necessarily stop at the same time. This one might descend at a greater rate than this one. So this one might start off faster, this one might start off a little more slowly, so this one stops before this one gets to that point. So the two would never have the same depth at the same time, at least not within the domain of both functions, because remember, after this one stops, we're done. Its domain is ended, and we can't compare the second function with the first at a time that's not in the domain. Now, it's entirely possible that this one starts earlier and then this one gets going faster and passes it up. So it's very possible that the two depths could at times be the same, or at least one time. Okay, well, how do you determine if the depths can be the same and whether they can? You set the y2 function equal to the y1 function. Here's the y2 function, here's the y1 function. Okay, setting those equal, now we want to solve for t to find out when the depths are the same. If we can find out when the depths are the same, then we can substitute that value of t back into the depth function, either one, and figure out what the depth is. Okay, well, to solve this equation, how do we proceed? This equation, we can see, is not linear. How do we know it's not linear? Well, linear functions like 2x plus 5 equals 7x minus 4. Just plain old first power of your variable. If the variable's x, that would, what I just said, would be a linear function. If we have an x squared in there, it's not linear anymore. If we have a 1 over x, it's not linear anymore. Well, if we have a 1 over x term here and an x term over here, it won't be linear. So, how do we solve this equation? Okay, it's not linear. Not in the form at plus b equals ct plus d. These are linear expressions. First power of t, polynomials with the first power of t only. Polynomials of degree 1. Okay, it's not in that form because of the t squared terms. Okay, t isn't in an exponent, so we don't have an exponential equation. There are no logarithms. There's no t in the denominator. Okay, so it's not logarithmic. It's not, if there's a t in the denominator, there's a good chance we have a rational function. But what is it? Well, okay, that thing is quadratic. Okay, now people had a lot of trouble understanding that this is a quadratic equation. Quadratic equation means you got a t. It's polynomials of degree 2. Okay, and an equation makes the equation a quadratic equation. So we can solve this. We solve it by putting it into the form at squared plus bt plus c equals 0, and using the quadratic formula. Well, if we do that, well, we can just subtract this whole side from both sides, which will leave us 0 on this side, and will leave us, well, this on the other side. I'm not going to read it to you. You can subtract this from this, and this is what you're going to get. So we solve for t using the quadratic formula, and again, I've written it out. It's just a matter of plugging in to the quadratic formula. But we find that the discriminant, and we need to know what a discriminant is and how it's important in finding the solutions of a quadratic equation. The discriminant, this expression under the radical, the b squared minus 4ac thing, okay, we're taking the square root of that. If this quantity is negative, the square root is going to be an imaginary number. It's not going to be a real number. So we have a non-real solution. And in this case, of course, the discriminant is 0.1 squared minus 0.02. And 0.1 squared is 0.01. And when you subtract 0.02, you get negative 0.01. This is negative. So there's no solution. Which means that y2 is never equal to y1. And the depths are never the same. Now that can happen. Okay, it can happen if this parabola is narrower than this one and remains above it. That's the case for this function.